So this is example number 1 for stresses, how to find the principal stresses specifically. So for this particular example, we want to find the principal state of stress for the following state of stress. So the following state of stress is given. Let's say this is KSI. Okay. So the first thing we want to do is the description. The description in this problem is state of stress is given. Okay, and obviously you want to assume that your body is in equilibrium. Number 2, going through your 6-step process, what we really want to do is we want to find sigma 1, sigma 2, and sigma 3. Step number 3 is the it is the theory, and we're going to use a variation of equation 3.15 of your textbook. And sorry, changed these colors mistakenly. Step number 4. So when you do the step number 4, you can find what your is the solution. You want to solve the whole problem. And if you solve it, you find I sub 0 is equal to 25, I1 is equal to 50. This is KSI. This is KSI squared. Sorry, this is 1, this is 2, this is 3. This is minus 1000 KSI cubed. So your equation looks like this. Okay, this is going back to the equations I gave you last time. And if you solve this, you can show that your sigma 1 is equal to 20, sigma 2 is equal to 10, sigma 3 equal to minus 5. Now, I want you to pay a close attention to this. So let's take this. Let's bring it right here. And let's take the solution and let's bring it right here. So what's really going on? First of all, one thing that you have to notice before I started the problem, you have made your life a lot easier if you realize that these were all zeros. If you realize these are all zeros, right? So the problem, I only have diagonal values. So when I have a diagonal values, that's a principal state of stress. So actually, my principal state of stress is always given by sigma 1, 0, 0, 0, sigma 2, 0, 0, 0, sigma 3. This is your principal state of stress. And you can see I don't have diagonal numbers. Actually, they are in the order. Sigma 1 is bigger than sigma 2, bigger than sigma 3. If by any chance somebody told you that your principal state of stress, let's say, was equal to minus 5, 10, 20, right? You immediately going to say this is a state of stress, but it's not principal state of stress. Okay, why is not principal state of stress? Because to be principal state of stress has to follow sigma 1, that has to be bigger than sigma 2, it has to be bigger than sigma 3, be all other zeros. Now, you may wonder how I got this answer so quick. Well, I just saw the state of stress, got the answers. Also, if you wanted to, you could always go ahead and do this in MATLAB, in the MATLAB code that's on your website. So when I solve this, you're going to open this file that's called principal. Let's close all these. So you're going to open the file called principal stress, okay? And you're going to run it. So you just press run. And when you're running it, it's going to ask you, are you working in inches? Yes, I am. This is KSI. So I press 2. Now it's going to ask you for state of stress. So if you remember from the problem I just gave you, the problem I just gave you is 20, 10, minus 5, you see, XX, YY, ZZ, all others are 0. Okay, it's going to only ask you for 6 because this is symmetric. Okay, so when you press enter, this the code will give you the Moore circle. I will teach you. I'm going to go over that in a minute. But then if you open this file, this is an output file, and you can see in this file, it gives you everything. It says this is your state of stress. This is your stress invariance, how they are calculated step by step. The replacement of this is 50. This is minus 1,000. And this is the characteristic equation that's given in this form. The characteristic equation is actually given by this, okay? So then this problem I basically did it using the long form just to show you how it's done. So replacing all the values, you get this. You could have also done this using MATLAB command called roots. So basically write roots, square bracket 1 minus 25 space 50 space minus 1,000. You may be asking why I always have a parenthesis. Nothing particular, just this is a generic code. So whenever there's a minus sign and I don't put down, you have minus minus, gets a bit confusing. So Z1, Z2, Z3 is also given as follows, right? Then the principal stress actually is equal to S1 is the maximum of these values. This is 20. S3 is the minimum of these values, is 5. Then S1, S2, S3 will be as follows. The principal state of stress is given by this equation, and I'm actually printing out for you what the state of stress looks like. Okay, if you wanted to know the maximum shear, the overall maximum shear is what we usually care for. There always will be 1, 3. There will be S1, S3. Okay, and so one of the advantages of doing this, finding this, you can also you can draw the Moore circle using reverse engineering. So if I know this is sigma, if I take tau positive upwards, right? And then I know my first value, my values are 20, 10, minus 5. So minus 5, 10, 20. So my first value, sigma 3 is here, sigma 2 is here, sigma 1 is here. Now you know that your circle, the midpoint of the circle is, midpoint of this is going to define the radius of this circle. The midpoint of this is going to define the radius of this circle. And then you're going to have a big circle. this is your famous Morse circle. Okay, and what you can see from this problem is what happens from here. This is tau 1 3, this is 1, this is 2, this is 3. This will be tau 2 3, this will be tau 2 3. Sorry, 1 2. So this is how you draw the, this is the easy way to draw the Morse circle. However, the code that I gave you in MATLAB actually draws the Morse circle for you and gives you these values that you, gives you this value. This is 20 minus 5 and gives you the maximum value. Okay, so this basically wraps up example number 1